Welcome back, everyone. Famous words of the day. And we're here for the last session of the day. We have with us Jakub Marchwicki. First of all, Jakub, hi. Am I pronouncing it right?
Uh, that's tricky part because the real pronunciation is Marchwicki with a very strong R, as we do in Polish.
All right.
But how we pronounce it is a classic English. Everyone that is English speaking, that's. Though if you probably pronounce it as if it was Romanian, that will be slightly closer to the real pronunciation. But
I tell you what, because Jakub is also is going to be a speaker with us now, but also on the Java conference. That's end of the month. So by that time, I promise I'll practice and I'll get it right in Polish.
we can give it a try. It'll be fun.
I love the confidence you have in. All right, I'll try not to disappoint you, but yeah. So we're going to talk about microservices, right?
Yes, that's the idea. Though this is not entirely about the microservices as we know that, like not about the frameworks and not about very concrete approaches to the certain problems. It's more about the general approach, what you can expect when you decide going into microservices, and all of those decisions that you will have to make.
In order not to be sorry at the end, right? When you end up with thousands of services and you need to manage all of them.
If that's what you need and that was your decision to have thousands of those, that's fine, because if that was a conscious decision, then you probably have all tooling and infrastructure around it to have it done right. But on the other hand, if it was totally accidental, it's an accidental complexity, and we have another problem.
Yeah, exactly. If I recall, I think JB Reinsberger was mentioning this when he was looking at essential complexity and accidental complexity, and most of the time, accidental complexity rules.
Yes, that's exactly true, because how I see it is very often when an engineer wanted to solve a simple problem, they were not looking where to put the solution, what's the right place to the solution, but they usually thought, oh, it will fit somewhere over here in the code base, and put it. So when you had a monolith, it was not good, not ideal, but it wasn't extremely bad. You just had a more in-memory calls or data on the other part of the disk. But if you get into a microservices environment and your other service is over HTTP in the other part of the globe, then yes, this gets problematic because the accidental complexity costs you a lot. And yeah, it's evening time in Poland, so you might overhear my two kids that are playing around. But they decided to just visit me whenever I have a conference call or any presentation.
Well, glad to have them. All right, but then, yeah, let's not take more of your time. Please, let's start the show, and then we'll get back at the end.
Yeah, so this one. Let's share it. I will double check it if it's working. Yeah, so this one. Let's share it. Oh, perfect. Something. Okay, I can take off my headphones. And I think I can give it a go.
Yeah, we see your screen.
So hello, everybody. This is very exciting time for me because this is first time ever I'm doing a totally online presentation. I know it has been half a year of a pandemic, and people should get accustomed to that. But I decided to give it a break with all the presentations. So now we are fully fledged and open for something new. So wherever you are, I'm saying hello to you. This is quite an interesting take because I'm sitting here, you're sitting over there, and we somehow communicate with each other. It'll be interesting. I'll have to make sure that my camera is also on. That's not the word to do this. Well, let's get started. Yeah, this is me. So, not taking much more of this precious time, we are here to talk about microservices. We'll be talking about the 5 whys of the microservices. So why microservices? Why microservices? Then why did we make ourselves so miserable with all this microservices? So my name is Jakub Marchwicki. As Dan said, I'm a software engineer by passion and by craft. And I do work in an online remote environment, which you can judge easily by the number of cats on my Instagram picture. So, how it all started with the microservices. Sorry, this is all getting weird. How it all started. One day, a lonely architect was sitting in his tower made of ivory and full of uncertainty and sadness, and the architect said, "Let there be microservices. Let there be small modules which have only a single reason to change. Let the modules communicate over a well-defined interfaces, and the output of one module becomes the input of another." And the architect saw it, and it was good. And the architect has given it a name. The architect called it a distributed system. And developers seen it, and it was good. And that was the evening and the morning. So, yeah, a little bit blurpy, but this is how we see the microservices trend and the microservices environment. All this blurry marketing, the gibberish. So let's get a little bit more concrete. So the microservices as the approach, it's not an architecture, it's the architectural approach, and it's already coined by Michael Toller in the beginning, like 2014. So that's an approach to develop a single application as a set of small services, each running its own process and communicating in a lightweight mechanism, often over HTTP API. So now somebody might say, well, putting lightweight and HTTP in a single sentence is already against common sense, but let's leave it. That's the definition. And people like it. So let's define it further. Microservice. We call it microservice because there is a small business domain, which is an independent service, independently deployed. It runs its own process. It manages its own data, and it's loosely integrated with all others using common communication protocols. Yeah, even more. And we all did it because monoliths were bad, okay? And microservices are good. Microservices are good because it's clean code. Yeah, that's what they say. It's a single responsibility module, potentially. It's much faster than monolith. It's faster to deploy, it works faster, yeah. It's easier to manage because in theory we have an independent team and independent code bases, and it's easier to scale. Yes, it's easier to scale at this point. We should at least mention Docker. Yes, Docker, and microservices are good, right? Nah, not right. Because if we really look for a definition, and I like definitions, we can say that we are talking about a collection of task-oriented or dedicated systems that pool their resources and capabilities together to create a new, more complex system which offers more functionality and more performance than simply sum of constituent systems. A very nice definition. However, it's not a definition of a microservice. It's a definition of the system, of the systems. And system of the systems is something that we already know for years, from 70s, from cyber physical systems. So an example of a system of systems is this. Is a Boeing 707. It has 7 million lines of code altogether in a flight control systems working independently between different devices and collaborating altogether. So we as software engineers say, yeah, we can get to the same level of safetiness as 707. On purpose, I did 787, not 737, but that's a different story. But we say, yes, we want to go for this microservices. We want those many systems working all together. So what can possibly go wrong? I found an illustration which shows the inter-process communication in our recent microservice deployment, and it looks like this. Yeah, what can possibly go wrong? So let's get to something more concrete. Imagine a system. Imagine how it usually works when it comes to microservices. So we have a service, a resource service, something that we are calling, something that holds the information we would like to query it back from. And then we have some other services. We have something to keep in access control, whether we can call it or can't. We have a user repository that holds all the users' entities. And we just call it. So we call the resource service, and it goes to the user's repository saying, oh, well, I have this guy here, and just want to make sure that this guy is really this guy who sent. And then we can go back, and then we go to access control to check, hello, can he access the resources? Can they access the resources that they want to? And then say, yes, they can, and I can get the answer. Obviously, this is a very naive approach, but well, it's fine. We'll do this 40 minutes presentation. I'm not a developer evangelist. If I were, that would be probably as far as I would have gotten. But no, and this is just an example. But what happens if the number of those resources like 15K? If there's like lots of resources and there are lots of users, with this approach, we already have a significant problem, an N+1 select problem, but now over HTTP, something we knew from ORMs now taken to the whole new level, and not latency between us and the database, but the whole network latency. Yeah. So what can possibly go wrong? The way we end up with this approach, or we end up with this architecture, is usually because not that it's like an anti-pattern and we build it on purpose, but it's because we build the system gradually, piece by piece, and layer by layer, system by system, and component by component. This is called a piecemeal growth, and is the process of building something step by step. Each step consists of evaluating the current system, deciding what should we do next, and then do the next one. And it was coined by Christopher Alexander, a guy that has nothing in common with the IT society, though his very famous design patterns book was then stolen by the IT industry because he was an architect, like a real architect. He was planning towns. Wonderful. So our architecture evolved. If we look at things in retrospective, yeah, then we'll see how they evolve. But it's very hard for us to look forward, to see how we should be building things from them to evolve nicely. Because microservices and building this piecemeal growth architecture is not a single shot. It's more of a journey. we have to decide how to go, and it's a road, and we have to go step by step. But let's get to this example I started with, a very naive one, and trail it down further. So we ended up with this. Yeah, it was a piecemeal growth, step by step, and it's all nicely. But we ended up with this. So what can we do? But first of all, I think we have to realize that what we've built is a distributed system. And distributed system is something, it's a system in which a failure of one computer, I didn't even know it existed, can render my own computer unusable. It's Leslie Lamport from 1987. So if we take this naive approach, if we have this set of services, at what happens if something fails? Because most probably it will fail. And why I say most probably, because there's another famous paper from 90s this time. It's called Fallacies of Distributed Computing, which is a set of assertions made by Peter Dutch and some other people in Sun Microsystems, describing the false assumptions that we as developers, we as programmers have when it comes to distributed applications. So if we look at them one by one, it's like network is not reliable, latency is non-zero, bandwidth is infinite. Well, that one we know if we go to the cloud. Network is secure. No, it isn't. Topology doesn't change. There's one administrator. Transport cost is 0, and network is homogeneous. Yes, we all know it's not true. But in other words, network sucks. So if we have this idea of multiple services, and we don't want to render our service unusable when some other computer fails, what do we do? Well, we load balance all the things. That's for sure. But if we load balance all the things, we have to choose the right load balancer. And this way we come to decisions when it comes to microservices. So before we chose load balancer, what can we do? Well, depending where we are deploying, what service, what environment, what cloud provider, and so on, we have a variety of options. We can go AWS, they have Elastic Load Balancer as a service. We can go Nginx, we can go HA Proxy, we have load balancing on Kubernetes if we are on Kubernetes, but we can have Ribbon and Eureka as a Spring JVM tooling, or we can Ribbon as a HTTP client and console for the discovery, and so on, and so on, and so on. Millions of options. What to choose? So, well, if we come to a load balancing, the concept is fairly easy. We have our service on one hand side, we have a load balancer, which encapsulate all the other services that we have behind it, and we have something centralized, a repository, or a system which holds all the information about all the services that can be called, so that our service is completely decoupled from the physical location of the services we are trying to call. But this load balancing approach has a name. It's called server-side load balancing. So now you can ask, if that's the first time you've encountered that, why it's called server-side load balancing, and if it has a very significant name, are there other types of load balancings that we have to take into consideration? Yes, there are, because there is a client-side load balancing. It's where our client has all the information about all the services we are able to call, and then we, on the client-side, load balance things. Notice that there is no central server. So if we get down to the definitions, we have like server-side load balancing or server-side service discovery. So the service registers itself in a central repository, and other services have access to the repository and internally forwards, and this repository or this load balancer internally forwards the request to an available instance. On the other side, the client-side load balancing, so the service registers itself in the repository, and the repository provides the information to other services. And other services can request the information and autonomously decide which instances are called, whether they want this kind of load balancing algorithm or that kind. It's like a sticky session or round robin or whatever. Yeah. So what to choose? What's the difference? What's the substantial difference, and why we have to figure it out? Well, there is a famous theorem about it. It's called CUP theorem. That for a distributed system, or for a distributed computing system, it's impossible to simultaneously provide all three constituencies, all three guarantees: consistency, availability, and partition tolerance. Right? We all know it. We all know CUP theorem from the database things, if we get more into database stuff. However, it also applies to other network services. So consistency. Every reads receives the most recent update, the most recent write, or an error. So if I cannot provide it, I fail. Availability. Every request provides a non-error response without a guarantee that it contains the most recent write. And then there's partition tolerance. So the system can continue operating despite an arbitrary number of messages being dropped or delayed by the network between the nodes. So now we have CUP theorem and the network fallacies. So we know that we can be either consistent or available or partition tolerant, and we know that network fails. The network doesn't work. And does it bring us any closer to a decision which load balancer should we use? Well, it is. It does, because we can either be consistent or available when partitioned. We cannot do both, and we again know it from the database environment. So if we take about consistency versus availability, if we have a CP, all data is consistent. So if we have an error between communicating between nodes in the consistency model, we get an error. Why am I talking only about the consistency and partition tolerance? Because partition tolerance in the distributed system is something we need to take for granted. So if that's AP, then we get an error. If that's consistency versus availability and it's AP, so all the data are distributed, but there's a error in the link, we just get the answer. We don't know if that's the latest write, if it isn't, but we at least get an answer. Let me run it by a human-friendly example. Imagine I'm sitting. Now it's possible. Imagine I'm sitting in a coffee shop, in the restaurant, or in a bar, having a coffee with a friend of mine, and we are working together on the presentation or something like this. And we are old-fashioned a bit. We are drinking a drip coffee and making notes on a paper, just brainstorming together some ideas of another distributed system presentation. We're pretty much into the flow, but they're closing the venue. Unfortunately, I live nearby, but a friend of mine lives quite far away, so we decide to continue talking about the subject, but over the phone. I call him, and we just split and go into different directions. Eventually, we became a distributed system. He's driving a tram home. He's driving a tram home, making some notes. I'm discussing that over the phone, and suddenly, his phone runs out of juice. His battery dies, and we have a network partition. I decided to continue working on the script because I was really into the flow. So I was writing down. I get back home, continue writing, and after like an hour or two, my wife came over and say, "Honey, you spent whole afternoon in the coffee with your mates, and now you are back at home, and you're still writing. Like, what are you doing? What are you so passionate about, and why are you spending so much time about it?" And now that's the decision time. I can be either available or consistent. Now, having said that, in the context of a wife is a really dry joke. I need to do both. But in this particular case, I can be either consistent and say, honey, I cannot contact my mate who I've been working with. Therefore, I cannot tell you what I'm working on, because what I might be telling you might have been irrelevant. Sorry. And we all know that's not the perfect approach when it comes to talking with your spouse. So we take the other approach. We can be available. We can say, honey, I can say, honey, I'm working on this presentation. I can run it through. I can run through it with you. However, keep in mind that I've been working with some other folks, and I have no connection with them. So what am I telling you might be irrelevant. Just a different approach. But I hope you see the difference. So, what load balancer should we pick? What load balancer should we be taking? But we can go further. Okay, we decided that we are rather AP because our environment is not doesn't need strict consistency. We are not a bank, and we are not a bank where client will be upset that he hasn't seen, or they haven't seen his latest balance. We are more of a social network. When a slight delay in posting a comment or posting a like to a cat on the Instagram, it's fine. So that's a difference. However, that's not all, because CAP theorem only tackles a problem of partitioning. But then, when it comes to absence of a partition, we have to choose either latency or consistency, because it may come to a situation that there is a connection, but the network is so laggy that the network or the other node is so flaky that we are not getting the response in time. We are just waiting and waiting and waiting. And then we have to decide whether I have to wait indefinitely and have a consistent answer or an error, or I don't want to wait. And once the answer is not here, I just time out and take whatever I have. And this again is called Pascal's theorem. So we used to ignore the consistency latency trade-off, and it's an oversight, as it is present at all times during the system operations, whereas CAP is only relevant in the rare cases of the network partition. So yet another context to a simple decision: how to build up a network and how to load balance things. So yeah, I hope you start getting the point where I'm heading. I said that microservices is a journey, and for every journey, you need a map. And you don't need a map to know where to go. You also need a map to know how to come back. And we are talking about the journey to microservices. It never starts at the day one, and it's just a matter of millions of decisions. Decisions that I just described. Decisions that seem to be fairly easy. Yeah, we all go with HA proxy, but decisions that have very significant consequences. And yeah, those decisions are not trivial. And the thing is that we, as an architect or as senior engineers or people who are overlooking this kind of an architecture, need to build up a log so we know why we've made certain decisions. Because the process of building the environment, the software, the process of building the whole infrastructure is a lengthy one. And we quite often get to a point where somebody challenges some architectural decisions or design decisions in the system, and we're just thinking, yes, I remember talking about that. I remember, and we made this decision, and we had those options, but I can't remember exactly what it is, and we just come up with this. So we need something like breadcrumbs on the way that will tell us and guide us back why we get to this point and how. Because architecture is a set of decisions. And we as engineers, we as people who are looking after this environment, need to document this decision, need to have a log. Because, say, you're choosing a NoSQL database, and you have this Mongo versus Cassandra versus React versus whatever else, and you end up with Mongo. And then after half a year, somebody comes over and says, why you've chosen Mongo? It has this and this problem. And you know that it has this problem, and you've decided to choose it because, yeah, you don't remember, because you haven't logged it. And for example, this decision might be based on something as trivial because, quote, we made a spike and we decided to see which database we can set up production ready within a day. And Mongo won, because it has best tutorials, and that's why we've chosen to use Mongo. That's not the ideal word, but it's good enough. So we are talking about the architecture decision records, and that's something that has been already coined by Michael Nidgard. So the architecture decision record is a kind of a document that captures an important architectural decision that was made, along with its context and the consequences. And it can be written in whatever form. It just has a title and status, yes, it was taken. A context, we are looking for a database to store session data. That's the context, and we chose Mongo. That's the decision. And then the most important, the consequences. If you, because the ADR, the architecture decision records, is getting some traction at the moment, you can easily go to GitHub and type and find some decisions in the open source environment. Just to give you an example, it's a from the Arcane web framework. I think it's a closure framework. They had to make a decision to abstract to build up the abstraction on the data, like data abstraction model. So there was a context. There needs to be a way for modules to speak common language for data manipulation and persistence. So they made a decision that they will provide a lightweight model, and it has some consequences. That different modules will define the structure, and there will be some basic persistence and so on. And so forth. And same with load balancing. We say we decided to go for a server-side load balancing. And now we have this central point which encapsulates all the other services. And then we have the consequences. And one consequence is a single point of failure. Like our HA proxy, no matter how solid it is, because it can fail. It has bugs. It has bugs. So it can fail. And then the another one, if we are encapsulating a number of services through a server-side load balancer, how can we access a very particular one? Because, for example, we would like to stop message consumers on each and every service. We can either know the exact IPs of the services, or we can expose some toggles, some admin endpoints to stop the queues. Well, if we expose those endpoints, then we have like 5 nodes, and we have to hit them via load balancer, just repeatedly looping until all the services are stopped. Some decision to make, some consequences to some consequences, because if we don't have this log, we end up with an architecture which is roughly described by the Heisenberg Department of Physics. We are probably somewhere over here with this architecture. That's how you can define the architecture without any decision to track whatsoever. And after some time, that's a big problem. That's a big problem. And this load balancing is not the only decision you have to make. There is more. There is much more. If we take our example architecture, we already have a few questions that we can ask over here. It's a very simple example, but it consists of 3 servers. So we have to understand if the services are even working. That's one thing. And it is good to know what's the request flow between the services. Is it right? Is it bad? Is it going somewhere weird-ish because of, I don't know? And are these services still compatible with each other? In old good times of monoliths, when we did change an API, the program didn't compile, didn't build. The test did fail. Now, in this microservice environment, the communication is going over HTTP. So no more compile time validation. We just don't know. Maybe somebody changed the API, maybe the request has changed, maybe the response could have changed. We know it when we deploy it, and that's definitely too late. So let's drill it down by one, because that leads us to yet another set of decisions. So are the services really working? Are the services even working? So again, well, we say, let's have a monitoring system. And then we have another. Should we use Prometheus, or should we use Grafana, or should we use Graphite? Yeah, another decision. That Prometheus is a more modern system. It's written in Go, whether the Graphite is in Python. Graphite is just a time series database, and Prometheus has everything around it. But then Grafana is a push model, and Prometheus is a pull model. So Prometheus has to get access to our services and has to know the location. So I have somehow to expose that my service is available for pulling. Whereas in Graphite, I just push the data no matter where am I. Significant difference. And then the way they store the data for Graphite, every matrix, every key is a huge matrix of like 60 megabyte in Whisper, which contains all the information, and Graphite is just filling it with data. And Prometheus is compacting the data on a regular basis and like every 2 hours, so it's more efficient data size. But do I really care? Well, I do have metrics around all my REST calls, and they include the user ID. And if I don't template the user ID, then I'll have millions 60 megabyte matrices in Graphite, which will kill my server and run out of disk space, right? So again, decisions, with something such simple as how to monitor. Yeah, but how to figure it out, how to start exploring this environment, because I want to go microservices, but I don't know yet how, I don't know what I need. How should I start? Well, monoliths are just slightly less distributed systems. You have external databases and so on and so forth. You have web front-end, back-end, and you still can use monitoring to figure stuff out. And then I am this microservice environment, and I have this request flowing here and there. So how can I trace it? Yeah, people say Jaeger, people say Zipkin. Yes, both are valid options. Both are based on Dapper, a Google paper, and both are there to send out information about each and every part of my request. Though the Zipkin is single deployable unit, I can just deploy it as a single instance. I have a connector, I have a collection of logs, querying of logs, and so on and so forth. And Jaeger is something coming from Cloud Native Foundation. So if I am already on Kubernetes, that's probably Jaeger's approach with all the sidecars and all the distribution is better for me. But how do I know? You know, because what I ultimately want to know is to let the application tell me where it spends time. And no matter whether it's a monolith, whether it's a distributed system, I can already use it. I can explore these tools before getting fully fledged on the microservice environment, and therefore have some information, have some knowledge to make those decisions. And last but not least, how do I know if the services are compatible with each other? And then I have Pact and I have Spring Cloud Contracts. You know, both do the same way. Both do the contract testing, and both supports HTTP and messaging. But which one to choose? What should be the reasoning to choose one over another? Like what decision? Pact is a polyglot, support natively multiple languages. Spring Cloud is more of a JVM based. Pact is Broker based. I have another service to maintain, and Spring Cloud contracts are not. Spring Cloud contracts are just Brokerless. I just dump contracts into a repository. In Pact, it's like purely consumer driven. My consumer can, in bad situation, in not ideal situation, cost failing of the producer. Whereas, on the other hand, Spring Cloud Contracts is all about collaboration and both consumer and producing building up from a contract that we collaboratively prepared. So yeah, keep things separately, but still close enough. That's the essence. Whether I choose one or another depends on the environment. It's just a matter of knowing and understanding the basic concepts that are behind the system. As we drill down the load balancing, there are many other ideas which we need to explore. Otherwise, we'll get this Heisenberg Department of Physics. And yes, this probability that we are here will be smaller and smaller and smaller. So I hope you noticed that even though microservices seem simple, a single service is a very simple. They aren't easy. There is a lots of to discuss and explore. So I hope there are some questions. Let me take headphones. Yes.
Yeah, cool stuff. I think the only thing I did not agree with you is that where you said microservices seem simple.
Yes, that's how yeah, that's the first side, and then there is this complexity I've talked about.
You know, it's a bit funny regarding Dan's question at the beginning. I'm sure you were referring to Netflix, Dan. We were having a discussion earlier on about how Netflix refactored their. I think they had 2 or 3 monoliths some 7 years ago, and they managed to create something like 2,200 microservices out of them.
Yes, so, that's true, so yes, and contributed a lot of tooling. The whole Netflix library for microservices. It's impressive, but very opinionated, but impressive.
Yeah, they do have. I really enjoy how they open source everything, or well, most everything, a lot of things. But
yeah, a lot of things.
I was wondering, what's your opinion on their approach to fixing their 2,200 microservices in creating basically some sort of a domain layer, effectively encapsulating the domain-specific microservices, basically. So something like object-oriented programming, but with HTTP requests.
There is an approach proposed by I think some German consultancy. It's called self-contained systems, where we are not talking about the microservices as in Netflix, so 20,000. We are more talking about smaller size monoliths that encapsulate, as you described, a single domain concept, whether it's like in financial environment, let it be a process of setting up an account. That's a kind of a single process. So the idea is to not to model the services around the domain concept or an aggregate, more of a model domain concept around Saga, about some long-standing processes that can work. That way you achieve one very important thing, that your service, your module, your part of the system is strictly consistent, because on the level of Saga you get a strict consistency, which in some cases is ideal. In some cases, though, 22,000 is fine, because the ultimate answer to should I go this way or should I go the other is what I am getting, what costs me more, whether it's more costly to have an inconsistency in our system and therefore have some financial troubles or compliance troubles, or if I have to scale the teams, and I do want teams to independently work on different things and move fast, and then figure out what's the mess. And Uber went for go fast, and they are totally evolving their platform in a enormous, insane speed. But they have lots of problems with consistency. And on the other hand, we have more financial institutions. So that's a very good word. It's a very good time for consultants. It depends. And we have to figure out whether it's one way or another. Which I hope answers your question.
Yeah, it does. Basically, you're saying go crazy with microservices if that's what you want, but be conscious about it.
Yeah, exactly.
Make sure you understand the trade-offs.
Exactly, and even if you don't, just log what you've done, log the important decisions, because that will allow you to go back and revisit and make not another guess, but say, well, we made this decision based on that, and it's invalid, so we will go that way, and that's how the architecture evolves.
And I can vouch for the quality of their engineering. I keep looking at how smooth everything Netflix releases is. So all the application, phone, TV, whatever, and compare that to the HBO experience, which, wow, I can't believe it's this slow, but it rhymes. So yes, absolutely.
All right, but here's
no, I have so much more to say about my hate for HBO, Dan. Let me finish.
But I have an interview question. So basically, what's the hardest microservice-related decision you had to make?
The hardest microservice. I think that to keep things abstract at the moment, I think that's the hardest one is these that when you make them, you have the feeling that you will live with this decision for the next N years, or for the next amount of time, because that's not easy to change. So, like they say about the architecture, deferring this decision is the most important thing. The hardest one, I think it was about choosing the messaging platform in one of the projects that we've been building a few years ago, and we were about to decide whether we should go with Kafka or RabbitMQ, and we decided Kafka, and it was a bad decision because the model that we were supposed to support didn't really needed Kafka. And Kafka came with a huge amount of infrastructure overhead and complexity that we not entirely were ready to solve by the team we had at that time. So like Rabbit is much easier to maintain than Kafka, but we went for Kafka because we thought the ability to replay all the events from the log or from the significant part of the log was so appealing to us, but it appeared it never worked. So the hard decisions are those that you have this feeling that will stay with you for quite a while, and you know that if you fail on that one, it will be really hard to get back. That's probably one of the hardest one I ever had.
Well, yeah, indeed, and I don't know, when you talk about architecture, decisions related to architecture, it's that thing, because you don't want to jump into making a decision, because then it narrows down your options. But at the same time, yeah, everybody talks about, I don't know, the last responsible moment. So then,
yes.
But nobody knows when that is. So I think a better question would be, what's your process for making these decisions? How do you experiment, or what steps do you take?
It's just today that I've spoken with one of my colleagues about it, how we approach this kind of problems. One thing is deferring. So we have this idea. We know that we can possibly solve it by making these things. So we say, yeah, that's great, but we don't do it now because we don't need it now. It will be probably good for the future, but let's see. And then we either build a spike or try to do it on a small scale, ideally on production. So the small scale, we pick up a small service. For example, one of those decisions was let's go reactive with some part of our stack. So we figure out a small service that was underutilized. It was called every now and then. It was doing a pretty meaningful job. It was querying a bit of data and passing it over somewhere else. It was called every few hours. So we thought, we have some experience with reactive stuff, but we don't have it in this environment, in this production environment. So let's build this service totally up, like from up to down on reactive, and see what problems we encounter. So that was our spike. It took us like a few sprint of efforts. It was fairly safe because once we figure out the reactive plumbing around that was fairly easy. It showed us a lot of things that we didn't really thought about when it came to reactive. For example, one thing was some of the Java drivers for reactive access to the database don't have polling. So they open a connection to database on every connection, which was ridiculous for us. But yeah, these kind of problems that you not think of, but they are shown in the spike. So, but you did a spike, you get this code to production, it's working, you see what are the problems, what the memory consumption was, the memory usage, and so on. And you kind of learn on the job, but on a small scale. And then you can decide, okay, it worked here, so you can try it here and there, and then gradually roll it over. And there, then you kind of defer this decision, but you prepare yourself to taking this one through this set of small, let's say, proof of concepts. And that's the ideal word. That's the word where I would love to, well, where I'm working and where I'd love to work with making such decisions, because then I feel safer about those.
Right. Yeah, and as you said, I think microservices as an architecture makes it easier for you to just try things out all the way in production, because then there's more.
Yes, and in the monolith times, in the past times, I did those things in tests. So the test suite of my application was kind of this area that it never went out to production. So if something failed there, it wasn't mission critical. So it was a good idea to experiment with new libraries, with new ideas, with the new languages, or with the new frameworks to a certain extent. But now with the microservices, I can take it to the whole new level, which I greatly enjoy. That's from my personal perspective, one of the best things that can that microservices can offer you. If you're in an environment of a constant experimentation, that's an ideal word.
Right. Vlad, do you think you have more questions?
Or somebody, do I or somebody from the audience have more questions? And yes, we do. The audience has. Basically, could you please give some real-world examples of when you preferred microservices intercommunication over common protocols versus message brokers, or vice versa?
I used to have this versus, now I don't have this versus, because the environment we are currently in uses both HTTP and message broker. We are kind of using both. Obviously, when using RabbitMQ, you can do synchronous communication over broker, and I know people do it. But at the moment, the approach we've taken is the asynchronous part obviously goes through the broker, so all the events, all the comments, and well, all the events go through the broker. So information that something has changed in the system goes through the broker, because different parties can subscribe to it and consume it on that in the way they want to consume it, and all the comments goes through the HTTP. So if I want something from the other service, I just call it, and it gives me an answer. If it doesn't give me an answer, I have an instant feedback that it fails, is 404, is 500, and I, as a client, have an opportunity to do something about it. So it's like a mixture. It's not either or. It's kind of both, and then you can have most of it, I think.
Mix and match.
Yes. Though I think there was this guy. Here's a VP engineering, now I don't remember, maybe Snapshot. He wrote a JVM library called Drop Wizard, which was all about HTTP communication. And he said that, I know that HTTP is not ideal, but it's a good then first guess. And that's the essence of it. HTTP is so pervasive, it's just everywhere, and it's so simple that we can start with that. And if we measure everything on the way, we can figure out, oh, that's not performing, and then we can change it. Then we can make a decision of changing it. And the speed and velocity that HTTP gives us at the beginning is just insane.
Yeah, so basically also leave this for the last responsible moment.
Yeah, exactly. that's deferring a decision is the ideal attitude I can imagine from any software architect or any architect. Probably also construction workers and so on, if that's possible.
It's a superpower.
Yeah.
Well, we have some other questions, but I'm not sure if time allows.
Well, I can stay with you for a little longer, and I can probably answer some of those questions offline if that's possible. I've seen the slide do, but I'm not sure if that's feasible to answer that. I'll probably address some.
You can. I'm not sure if all of them are serious though. So for example, question, what's the best load balancer? I think the best answer would be it depends, right?
Yeah, the best answer is it depends, and why it depends I just showed in the presentation, because there are so many things to take into consideration that there is no definite answer. At the moment, I'm using, the environment we are using is having HA proxy, which is great until it isn't. Until we encounter one or two bugs that, for example, effectively cause all services for 503 for a certain period of time. So the answer is it depends. There's no definite answer.
No matter what you say, somebody's going to get pissed, and no, it's not right.
Yeah. Oh, that's always for sure.
Well, then I think this is it.
This is it.
Is this it? Is this the end?
It seems that way.
Today.
Seems that way. But we also have conferences for the rest of the week, and then Jakub will be back with us towards the end of the month. So there's still enough things to look forward to.